All right. Okay. Let's go through your questions on 6.5. Okay, so the first question was on 7C. Okay. So on 7C, the hope is, like, they use the word logistics, so that should bring to mind what we learned last time. Plus, okay guys, the derivative is given in the form, like that's the standard logistic differential equation form. And what we know about a logistic function, so once I see that, I immediately go, okay, the carrying capacity is 100. I'm expecting the curve to look something like that. The other key feature of a logistic, remember, is that it's like increasing the fastest or changing concavity at that halfway point. So when the population is half of the amount. So on 7C, it just says find the value of P when the rate of change is the greatest. The rate of change is the slope. The slope is the greatest at the halfway mark. So when P equals 50. They didn't even ask us to find the time. Time is harder. You have to find the intersection to find the time, but they just want P to be on that exponent. Okay. If I wanted to talk about like the top half or the bottom half, I could talk about where is the population like increasing at an increasing rate or increasing at a decreasing rate. So if I said, where is the population? For what population is the rate of change increase, is the population increasing at an increasing rate? Good, below 50. So if it was increasing at an increasing rate, you could say between 0 and 50, right? If I wanted to talk about above. So they could ask you various questions like that, but they're always going to be, yeah, pretty straightforward. Okay. Number 8, somebody asked about 8. 8 is a little less obvious because it's not in the form like number 7 was. We want it to be 100 minus P, or sorry, a number minus P, or whatever the variable is. In this case, they're using Y. So I want this to just be a variable. I don't want the 1 over 50. So I want to factor out the 1 over 50. I want to bring the 1 over 50 in front, which you can do. So we can have the 2Y that was in front. We're also going to bring out the 1 over 50. But if you're bringing something out in front, you're dividing by it. You have to divide both of them by it. So what is 1 divided by 1 over 50? 50. So the 1 becomes 50, so that if I multiply it back together, it's still 1. Okay? And then now I can bring out the 1 over 50 next to the Y. If I were to distribute, that is equivalent to the original. You could reduce it 2 over 150. Let's see, that's Y over 25 or 1 over 25 times Y. But the 50 is what we really care about. The 50 is that carrying capacity. So it asks us, to find K. What's K? Which value is K on this equation now that I got it to this point? The constant here, right? The 1 over 25, it's always, usually it's a decimal. We could write that as a decimal. The carrying capacity M is 50. And then it wants the logistic differential, or sorry, the logistic equation given the initial condition. You won't have to do these on your test or the AP test. This is going from like the Y equals equation. On the other page, they have it in your book written as the population as a function of time. We can just write Y. The formula is it's M divided by 1 plus C, and then e to the negative Km times T. Okay, you're not going to have to memorize that on your test, but you're just going to use this formula. You'll plug in K and M. So if we plug in K and M, let's see, I can plug in M is 50, and then here K times M. Well, K times M, that's going to reduce to 2, so it's negative 2 times t. So that's our population. In this question, they're calling it y, so I'll just say y equals this. And then on part C, it's just saying use this initial condition to find the logistic equation. So they're saying let t equal 0 and y equal 10. So plug in 10 for y and 0 for time. E to the t is 1, so this is just 1. So we really would have 10 equals 50 over 1 plus a constant. And you guys can like finish solving that for C. And that's all that they want to do is finish solving. Okay. So number 9, we need to ask on 9. 9 is pretty much the exact same thing. On part A, they want you to find a formula. Well, you're going to find the formula in the same way. To find the formula, you start with the population as a function of time is m divided by 1 plus a constant e to the negative k m times t. What's m on this one? Yeah, m is the 150. What's k? Yeah, this decimal right there, right? And then you're going to plug in the initial condition to find the value of C. Your initial condition on this one was, well, there were 6 guppies introduced initially. So your population equation at time t would be the 150 divided by 1 plus a constant e to the negative that decimal times 150, sorry, times t, running out of space. And then you're going to plug in 6 for the population when t is 0. And then you'll be able to solve for C. After you have that equation on part B, you just graph 100. So you're going to graph the equation that you have, whatever equation you have. So you're going to graph this function, and then you're going to graph 100, and then you'll find the intersection. And I'll tell you, I was looking ahead to your test. Your test is this Friday. Really, this one skill of finding an intersection is the only question where a calculator would be required. So the rest of your test, I don't think is necessary to be calculator required. So your test on Friday will be a no calculator test, which means I won't ask you a question like this since it will require a calculator. I could ask you logistic functions. It's just I'll stick with questions like, you know, given this, what's the carrying capacity? Or I could ask you about when is it increasing the fastest. So I could ask you some of the really basic questions you won't have to find the intersection. Okay, so your test on Friday will be non-calculator. Okay, and then you guys asked 2 of these integral ones, and they were really tricky ones. I was surprised how difficult they made these, especially number 13. There are 3 methods of integration that we have to apply in order to make it through question 13. You will never have one that's this time consuming on a test, but it is kind of fun to see, interesting to see how they were able to come up with a question that made us do so much. At first I thought, oh, they're so nice. They're telling us what U should be, so it's not going to be very bad. Was it somebody in this class who came up with the idea that the weird U sub is root U? And I like this. It seems to be holding a pattern. The weird U sub where like it's not our traditional, but if you let U be some root, and then you solve for x before you take the derivative. So we can solve for x by squaring each side. If we square each side, we can get to here. And then we take the derivative, so we get 2u du equals dx. And then we make the substitution. So we started with the integral, which was root x over x minus 1 dx. And we're just substituting everything into either u or du. Well, square root of x is just u, so the numerator can become u. The denominator, the x, well, x is equal to u squared, so u squared minus 1. At this point in the question, I was like, yes, this looks like it's going to be a u sub because the numerator is the derivative. But unfortunately, we also have to get rid of dx, and dx is equal to 2u dx. So I actually have a 2u du here. So basic u sub is not going to work. So then I thought, okay, well, the numerator, I can go ahead and multiply those together. So I can write this as the integral of 2u squared over u squared minus 1. So a traditional u sub no longer works because the derivative of the denominator is not what we have on top. What method of integration can we try now? Yeah, long division. Anytime it's equal or top heavy, you need to do long division. So long division, I'm going to take the u squared minus 1 and divide it into the numerator. Well, u squared times 2 would give us 2u squared, so I could put a 2 on top, distribute that down, so I get 2u squared minus 2. I don't think any one of like the particular methods in this question is that hard. It's just that they made us do all three. We change the signs. The first term should cancel. So we've got 2. So that's our remainder. Our rule is then, if we do long division, you get 2 plus the remainder over the original divisor. So we're really integrating that after long division. So at this point in the question, I'm thinking, okay, I'm gonna take this down. The first piece is easy. What's the antiderivative of 2? 2u. So currently, because everything's in terms of u, and I'll go back to x at the end. So my thing that's trickier is this piece. So I want to focus on, okay, I need to integrate 2 over u squared minus 1. Takes yet another method of integration. What do you guys think? Would basic u sub work? I always try that first. U sub doesn't work because we don't have a u on top. What do you notice about the denominator? We can factor it. If the denominator is factorable, then you'll do partial fractions. So that denominator, I notice, okay, well, I could rewrite that as u plus 1 and u minus 1. So then that means I want to break this up into 2 fractions. A over one of the factors plus b over one of the other factors. So as terrible as this question is, we can think, oh, good, we're getting practice on 3 different types of problems, types of integration. I want to clear the denominators. So I would multiply by the common denominator. So the left-hand side just becomes 2, it has both factors. The a has to multiply by the factor that it does not have in the denominator. So what is the a going to have to multiply by? U minus 1. And then the b is going to have to multiply by a u plus 1. And then we make our choices to get rid of the a or b. So I could start by letting u equal 1. If u is 1, a goes away. So I'd have 2 equals 2 times b. So b is 1. What else would be a good choice to let u equal? Negative 1. We do negative 1, we get 2 equals, let's see, a negative 2a. So a is negative 1. Now again, my a and b might be different than your a and b. Just make sure it's lined up with the correct denominator. So really this integral, this piece, is the integral of a. My a was negative 1 over u plus 1. And b, which was 1 over u minus 1. And now I can do the antiderivative of each of those. Because the derivative of the bottom is just 1, so it's just ln of that. This is negative ln absolute value of u plus 1 plus ln absolute value of u minus 1. We have a plus c, and we have this 2u from the beginning that's still hanging out in front. And one last thing we have to do. Yeah, just put x back in. So at the very beginning, we come all the way back, u was root x. So I'm just going to make that substitution. So my final answer, 2 root x minus natural log root x plus 1 plus natural log root x minus 1 plus c. So again, I would never put one of these questions on your test where you have 3. Any one of those individual methods, though, I think was fair. Long division was fair, partial fractions, weird u sub, all of those are okay. They're just all in one problem. Okay, the other question that you guys asked that was a good one was number 20. So on 20, we have this. What do you guys think? If I'm at a loss, I kind of go down the list. I can't do regular u sub. That doesn't work. But I do have that root x, which makes me think, could I do the weird u sub? So I'm going to try the weird u sub, which is u equals root x. And then what? What do I do to, just like the start of the last question? Good. We square both sides because we want to get the x by itself and then take the derivative. So now if we take the derivative, we get 2u du equals dx. And again, most of the time when I start an integration question, I don't know if this is going to work. I just kind of make a guess at one of the methods and go and hope that it works out. So I was at a loss of what to do, so I thought I would try this. Now I try to make my substitutions. So I have the 1/2, I have sine. In place of root x, I can write u. And in place of dx, we can write 2u du. I notice that the 1/2 and the 2 can cancel out, so that's a good sign. I'm just going to write the u in front, so I have u times sine of u du. Right here, I was feeling pretty hopeful because I see a product of two functions. One isn't the derivative of the other, so it's not a typical use of. But what was the rule we learned last week? If you have two functions that are being multiplied, what method can you do? Integration by parts. So the integration by parts, quick reminder, integration by parts is the integral of u dv equals u times v minus the integral of v dv. So ultraviolet blue. So you could do this process. If you did this process, you could say, okay, let u be lipid. So in this case, we have a polynomial in trig, kind of annoying because there's already a u, but you could let this be u and let this be dv. What's the other method we can do? What's the shortcut of integration by parts? Just set it. Tabular, where we do the two columns. So tabular is the shortcut of this, which works if one of the two functions you can take the derivative until you get 0, which we can't because I can take u and take the derivative. The derivative of u is 1, and the derivative of 1 is 0. So as long as one of the functions, you can take the derivative to get to 0, and the other function, you can easily find the antiderivative. What is the antiderivative of sine? Negative cosine. And the antiderivative of negative cosine? Negative sine. Tabular integration, we're following this pattern. So the first product is basically your u times v, and it was positive. So it always starts positive and then the signs alternate. First diagonal, positive. Second diagonal is negative. So you multiply these together. So if we multiply those, we have a negative u cosine of u. And then we multiply these ones together, but the negatives multiply and become positive. So I get a positive sine of u plus a constant. What's my last step I still have to do? Yeah, so we come back, make sure to finish by plugging that back in. So I would have negative square root of x, cosine root x, and sine root x plus c. Okay. I would say tabular is one that comes up every time. It's another one that if you haven't already done, that's going to be very similar on your test. Something like 19. These ones stand out to me all the time. So you always end up with one function that's like a polynomial where you can take the derivative to get to 0. They like to ask tabular questions with sine or cosine just because you can easily find the antiderivative. Okay, so a question like this is like a pretty predictable test question, something like that. So make sure you're comfortable on 19. So let me see if you guys had any others. Somebody asked about 24. Okay, great. 24. We're going to do this one the long way, and this is a good lead in to our shortcut that we're going to learn today, and it'll make you appreciate what we do today. Today's lesson is actually pretty easy. Okay, what do we try first? Anytime we do a limit, what's your first thing you try? What do we do with that -1? Just plug it in, right? So let's just plug it in and see what happens. If we plug in -1, we have the square root of -1 plus 2 minus 1 over -1 plus 1. Well, that would give us the square root of 1 minus 1 over 0, or 0 over 0. Yes. Oh, it's not on your assignment? Oh, good. Maybe somebody else put that in.
I think it might have been someone that.
Okay, so maybe that's it. Okay, well, this will be a good lead into what I'm going to teach you now. But you guys remember how we did 24 previously? If you end up with 0 on the bottom, how did we have to get rid of that square root on the top? You remember? It's a method we're not going to have to do in the future after today. In the past, you had to take this and multiply this by the conjugate, and you multiply by that. Kind of ringing a bell. It was pretty terrible where we just changed the sign. So we changed this from a minus to a plus and do the same thing to the top and the bottom. We multiplied and then we'd eventually be able to factor and reduce it. Well, if you're taking a limit and you do direct substitution and you end up with a case of 0 over 0, that's called an indeterminate form, or infinity over infinity, you can use our shortcut today. So we're not going to have to go this long route anymore. So I'm not going to focus on it. So I'm going to skip ahead to our new one. Let's look at L'Hopital's rule. I'll go back to that question maybe in a minute, but first I'll start with an easier question that just isn't as much algebra. So previously, if I'd asked you a question like, let's take the limit as x goes to 2, and I'm going to make it be x minus 2 over x squared minus 4. So we've been doing limits since the beginning of the year. You guys have evaluated limits like this since like the first week of school. Just like on the last one, I would do direct substitution. But if I plug in 2, I'd have 2 minus 2 over 2 squared minus 4, or I'd get 0 over 0. Okay, what have we done? How have you simplified this or evaluated this limit in the past? Yeah, I do. Say that again. Good. We would factor and reduce the fraction. So yes, we could remove that discontinuity because the denominator factors as x plus 2 and x minus 2. So that's a removable discontinuity. So if you can remove it, then you can say, okay, well, let's take the limit of the reduced function. We were able to reduce it to that function, and then we would plug in 2, and what would our answer be? 1/4. I had to teach you the long way because you can't do the shortcut way today until you know all of your derivatives. But now that we know everything, we can do the shortcut way. So the shortcut way is saying this L'Hopital's rule is if you're taking a limit and you try direct substitution, okay, so we always try direct substitution first. If it yields 0 over 0 or infinity over infinity, only in these two cases does this rule apply. But if that's the case, then the limit of the original ratio is equal to the limit of the ratio of the derivatives. So you could have just taken the derivative of the top and the derivative of the bottom and then done it and done it. So let me do it with this question. So I'm going to apply this L'Hopital's rule. Since it was 0 over 0, I could say, okay, this limit is really equal to the limit of the derivatives. What's the derivative of x minus 2? What's the derivative of the numerator? 1. What is the derivative of the denominator? 2x. Can I plug in 2 now? What would we get? Isn't that amazing? Right? So much faster than our last way. So if you can apply it, notice I did not do quotient rule. Sometimes I see students wanting to do quotient rule because yes, this is a quotient, but we're not taking a derivative of the whole function. It's just the top derivative divided by the bottom derivative. Okay, so this is L'Hopital's rule, that if the limit is 0 over 0, then the limit is equal to the limit of the derivative. But again, super, super important. It's only applied to those two cases. If it's not 0 over 0 or infinity over infinity, then this rule does not apply. Okay, so let's try this one. If I do direct substitution, I would basically be plugging infinity in for both pieces. I'm going to emphasize if this is on a free response, they tell us that you have to write these out as two separate limits. So I'm going to go the long way of the work that you have to show on a free response, but I would never do this on a multiple choice. But it's technically, you'd say, okay, the limit of the numerator. What is the limit as x goes to infinity of the top? What's the limit as x goes to infinity of x? Infinity. So the top limit is infinity. Then the limit as x goes to infinity of the bottom. Well, what's that limit? Infinity. So this is a L'Hopital's rule question. So on a test, I would have to write out, and I find this a little annoying too, they require you to write out the two limits individually. If I was doing this just on homework and like multiple choice questions, which is typically where these come up, I would just say, okay, well, wait, yeah, that's infinity and that's infinity, so L'Hopital's rule. So like that's okay on your homework, checking to make sure it must be an infinity over infinity or 0 over 0 case in order to do it. But on a test, if you did that, you wouldn't get full points for proving that you're using L'Hopital's rule. Does that make sense? I'll emphasize it again when we get to like test prep. But if you can apply L'Hopital's rule, then you can just say, okay, well then this limit, the original limit, is equal to the limit of the derivative. What is the derivative of the numerator? Sorry, derivative of x? 1. What's the derivative of e to the x? E to the x. Now we can plug in infinity. If I plug in infinity, I'd have 1 over e to infinity, which is really just like 1 over infinity. So what's 1 divided by a giant number? What was it? Really small number, what does it approach? 0. Very good. So 1 divided by infinity is 0. 1 divided by like a million approaches 0. Okay, so that answer is 0. Okay, if I try the same thing on 2, if I were to go to infinity, so I'm going to kind of show the shortcut, but I'm not going to, like not writing out the separate limits. I'm just going to avoid putting an equal sign in between because technically it's not equal. I'd have to show the wrong way. But if I take the limit to infinity, this top piece goes to infinity. So I'd say, okay, yep, the numerator is infinity. The denominator is also infinity. So this is a L'Hopital's rule question. So I can apply L'Hopital's rule, which means that this limit is equal to the limit of the derivative. What's the derivative of the top? E to the x. What's the derivative of the bottom? 1. If we plug in infinity, what would we get? Infinity. So this answer would be infinity. Okay. But again, I need to emphasize, don't apply this rule unless it's 0 over 0 or infinity over infinity. So on number 3, I'm going to do direct substitution first. If I plug in 0, the top is 0. The bottom would be e to the 0. What's e to the 0? 1. So this is really 0 over 1, which is 0. It is not 0 over 0. So don't try to apply L'Hopital's rule. You'll get the wrong answer if you take the derivative of the top and the bottom. Okay, so just don't apply it unless it's one of those two cases. Okay. The next question 4, is almost the same. I guess they flipped it, but we're approaching 0 from the negative side. Quick reminder, if you're taking a limit to a constant from the positive or negative side, you don't really have to worry about it if you can plug in regular 0. So like e to the x, I can plug in 0, so that's just e to the 0. That's fine. The bottom, I can't divide by 0, so I can't plug in 0. So I'm supposed to be approaching 0 from the negative side. So what's a number close to 0 but on the negative side? Yeah, like a negative 0.1. Well, e to the 0 is 1. So what's happening if we take 1 and we divide by a really tiny number? Because the closer we get to 0, the more tiny negative number. What is that going to approach? Negative infinity. So yep, this will approach negative infinity. If you divide by a tiny number, that's like multiplying by a big number. You can kind of think of this as like negative 1/10, right? So you're flipping and multiplying. So it ends up going to a positive big number. So that one did not require L'Hopital's rule. So don't think every question is going to require L'Hopital's rule. Start with direct substitution. And again, to kind of avoid writing bad math, I'll just do this separate without doing an equal sign. So I'm plugging in 0 for x and seeing what I get. Well, the numerator, e to the 0, that's 1. So the numerator is 3 minus 3, which is 0. So it is 0 over 0. So it is L'Hopital's rule. Okay, so it has to be 0 over 0 or infinity over infinity. If that happens, then you can set this equal to the limit of the derivative. What's the derivative of the numerator? The 3 just goes away, right? Derivative of 3 goes away. What's the derivative of this second piece? Good, a negative 9 e to the 3x. And then you just have to divide by the derivative of the bottom. What's the derivative of the bottom? 1. We try direct substitution again. So now we try to plug in 0. If we plug in 0, we have negative 9 e to the 0 over 1. E to the 0 is 1. So our answer is negative 9. Okay. So I would say L'Hopital's rule typically score really high on this. This is a concept that they keep taking in and taking out. It's been in for a few years, and yes, students generally do well. Sometimes you have to get a little creative though, because again, it only works if it's 0 over 0 or infinity over infinity. So right here, I would try direct substitution, and my initial thought is, okay, so this isn't like technical math. This is like my logic though, right? I'm plugging in negative infinity. Negative infinity squared is infinity. What's e to negative infinity? What does e approach if you go to negative infinity? Think of the graph of e. Here's the graph of e. As you go to negative infinity, where does the graph go? 0. So this is infinity times 0. Infinity times 0 is indeterminate. You might think, well, wait, infinity times 0 is always 0. Not necessarily. Like as we take a limit, it could be something different. So a limit of this product is indeterminate. we want to rewrite this either as 0 over 0 or infinity over infinity. So it needs to be a fraction of some kind. So I want to put one of these two on the bottom. You could do either one. One of them works nicely and one of them doesn't work nicely. So you just kind of take a guess. I'm going to choose to put this e to the x on the bottom. How could I move the e to the x to the bottom?
Negative x.
Good. So I'm going to write it instead as that, because I want it to be a quotient, because a quotient are the times when you could possibly apply L'Hopital's rule. So it's equivalent. Now let's see what happens if I take the limit as x goes to negative infinity. The numerator is still infinity. If I go to negative infinity on the bottom, I've got e to the negative infinity, which is really e to infinity, which is infinity. So now it is a L'Hopital's rule question. Does that make sense? So if it's a product of two, just move one of them to the bottom by using negative exponents to see if you can write it in a form where you can apply L'Hopital's rule. If you can apply L'Hopital's rule, that means that we can take the limit of the derivatives. What's the derivative of the numerator? 2x. What's the derivative of the denominator? Great. If we plug in negative infinity, what would the numerator be? Negative infinity, right? 2 times negative infinity. The bottom would be negative e to the negative infinity, or e to infinity, but that's still infinity. So this is still infinity over infinity, which is okay, doesn't matter plus or minus. That just means we do L'Hopital's rule again. So sometimes you have to repeat it a couple of times. If you still have infinity over infinity, you take the derivative again. Okay, so I repeat, what's the derivative of the numerator? 2. And the denominator, we just multiply by a negative, do the derivative, so it's going to become e to the negative x. If we plug in negative infinity, what's the numerator? 2. Doesn't change because there's not an x. The denominator is like e to the negative of negative infinity, which is really e to infinity, but what's e to infinity? Infinity, and what's 2 divided by a giant number? 0. So this comes out to be 0. You probably could have guessed that at the beginning because we said, initially we saw this as 0 times infinity. So my initial guess would be 0, but we're going to see some where it doesn't end up being 0. All right. So if we look at one like 7, we always try direct substitution, but if I do direct substitution, I see that as 1 over 0 minus 1 over 0. They're both like indeterminate. So it's tempting to just say, oh, this limit doesn't exist because each one has a 0 in the denominator, but not necessarily. This is where we want to try to apply L'Hopital's rule. So in order to apply L'Hopital's rule, we need this to be one fraction instead of 2 separate fractions. And then we can see if it would fit the 0 over 0 or infinity over infinity. What would we need to do to get this to be one fraction? Back to like, to add 2 or subtract 2 fractions together, what do they both need? Yeah, Isaac. A common denominator, exactly. So I'm going to choose to multiply the first fraction, top and bottom, by x minus 1. And I'll choose to multiply the second fraction by ln of x. My goal is I want to get them with the same denominator so I can write it as one fraction. So the first fraction has a numerator of x minus 1 and a denominator with both factors. Same thing on the second one, the numerator and the denominator has both factors. We needed to get a common denominator so that we could write this as one fraction. All right, this one is going to take a little bit of space. So I could write this as x minus 1 minus natural log of x all over natural log of x times x minus 1. Still taking the limit as x goes to 1. If we plug in 1, what's the numerator? What's ln of 1? 0. So the numerator is 0. If we plug in 1 in the denominator, what would we get? 0, which is good. That means we can apply L'Hopital's rule. L'Hopital's rule says take the derivative of the top and divide it by the derivative of the bottom. So I'm still taking the limit as x goes to 1. Let's just worry about derivative of the top first. On the top, we have this x, and the derivative of x is 1. The negative 1, the constant just goes away. What's the derivative of negative ln of x? Negative 1 over x. I'm not going to bother simplifying, so just leave it like that. Like I'm not going to simplify. I'll just do direct substitution. Now I have to do the derivative of the denominator. What's going to be a little bit of a pain there? What was that? Exactly. It's going to require product rule because there's a product right there. So you do have to apply product rule. So it's going to start to look ugly, but just kind of leave it ugly. So product rule says the first times the derivative of the second plus the second times the derivative of the first. Again, I'm not going to bother simplifying because I'm just going to plug in 1. My hope is I get a number out. If I plug in 1, what's the numerator? What would the top be? 0. So if we plug in 1 on the bottom, I have natural log of 1 plus 1 minus 1 times 1 over 1. What would that come out to be? 0. So that's good and bad. It's bad because we don't have an answer, but it's good because we can do what? We can do L'Hopital's rule again. Sure, it's going to look kind of ugly, but if you don't simplify, it actually makes it easier. So this tells me that I can now take the limit of the derivatives again. The numerator isn't bad. The 1 just goes away, and I need the derivative of this piece. Well, this piece is really negative x to the negative 1. So its derivative, the negative comes down, and we drop by a power. So there's the derivative of the top. The bottom is kind of a pain because it will require product rule when we get over to this piece. But the derivative of ln of x is 1 over x, so that piece is 1 over x. And then here I need to do product rule. So product rule says, you guys make sure I don't mess up. Product rule says the first times the derivative of the second, but the derivative of that would be negative 1x to the negative 2. So it's first times the derivative of the second plus the second times the derivative of the first, which is 1. Do you agree with my derivative? Okay, then you try direct substitution. So now we go, okay, well, let's try plugging in 1 now. If I plug in 1 now, I'd have 1 to the negative 2 on top. On the bottom, I'd have 1 over 1 plus 1 minus 1. Okay, well, that's great because 1 minus 1, that's just going to be 0, but I'll write everything out. So because this is 0, this whole middle piece is gone. What's 1 to the negative 2? What is this numerator? 1. So the numerator is 1. The denominator is really just 1 plus 1. So 2. So our answer is 1/2. That's like as bad as they get. That one was bad because it was L'Hopital's rule twice and product rule twice. They usually aren't that bad. Okay, 8 and 9 is just kind of doing what I started class with, which was showing you that you can do it. Here this is trying to say without L'Hopital's rule. So how did we do it at the beginning of the year? How did we solve one like this? Because if you notice right away that, it makes a 0 in the denominator, you can factor. What are the 2 terms on top have in common? A 2. And then we'd be left with x squared minus 1. How can we factor x squared minus 1? Good. So that factors as an x plus 1 and then x minus 1. We had an x plus 1 on the bottom, so we could factor and remove that. So you're still always welcome to do our previous methods. If that stands out to you like faster, go ahead and do that. We plug in negative 1, what would our answer be? Negative 4. And they're just saying, okay, well, now try that same question using L'Hopital's rule. Only okay, because if we were to plug in negative 1, we would get 0 over 0. That's why we're allowed to do L'Hopital's rule. So L'Hopital's rule says, okay, take the derivative, the limit of the derivative. What's the derivative of the top? 4x. What's the derivative of the bottom? 1. If we plug in negative 1, sure enough, we get the same answer. Okay, so it's just another way of doing this question. All right, there are several indeterminate forms. The only ones that work with L'Hopital's rule are 0 over 0 and infinity over infinity. But here are some that aren't quite in that form, and then we're going to kind of worry about how we could simplify them. So it's saying the following limits are not in these forms. Identify the form and tell which are indeterminate. So by the form, we're just going to plug in infinity. If I were to plug in infinity, 1 over infinity, this piece here would go to 0. So it's 1 to infinity, which is an indeterminate form. So this is indeterminate. You might think, well, wait, 1 to any power, what would your guess be? 1 to any power, what do you think that would be? 1. You would think 1, but we're actually going to evaluate this limit right here. I'll tell you the answer is not 1. So indeterminate means it might exist, it might not exist. We have to do some more work to try to rewrite it in a different form to make it happen. Okay, if we have this one, if we approach 0, well, this would be like a 0 to the 0 case. This is also indeterminate. We're going to use different methods. We could use different methods. It might be that it does not exist, but it might be that it exists. We have to investigate further. Same thing here. This would be infinity, 1 over infinity, which is 0. Let me make sure I'm saying this right. Yeah, which is also indeterminate. You might think, well, anything to the 0 power is 1, and yeah, there's a good chance it could be 1, but it might come out to be that it does not exist or equal to something else. We have to investigate. This one, if we plug in 0, we have sine of 0, which is 0, and then 1 to the, it ends up being to infinity. So 0 to infinity. This one, it does turn out is 0. This is 0. So if your base is 0, you don't have to investigate further. It's 0. It doesn't matter that it's raised to the infinity power. Yeah. If it's infinity to the 0, then it's indeterminate, but a 0 as a base stays 0. All right. So these two problems are kind of an extension of L'Hopital's rule. You only have to do this method. This method stands out to you when I have an x in the base somewhere and an x in the exponent. So again, an x in the base and an x in the exponent. I want to be able to bring that power down. And I would do this if it's one of the indeterminate forms, but we just showed that this is the case. So what I'm going to do is I'm going to start by saying y equals this limit. And my goal is basically, to solve for y. I'm trying to solve for this. But because I have variables in the base and in the exponent, I would love to be able to bring that power down in front. What can we do? What can we put in front so that it allows us to bring the power down in front as a coefficient? What function? It's a property of a function. Logs. Yep. So I'm going to choose to take natural log of each side. So because I want to do that, I'm just going to take natural log of each side. Taking natural log allows me to bring that power down and write it in front as a coefficient. So now I have natural log of y equals, I still have this limit. The limit just stays in front. I'll deal with that later. And the x came down in front, so it's x times natural log of that. Okay. So again, I'll do this trick whenever there's an x in the base and in the exponent. I wanted this to be a product because my hope is that I'm going to be able to apply L'Hopital's rule, because L'Hopital's rule helps us investigate these indeterminate forms. If I plug in infinity right now, I would get infinity times what? Natural log of 1. So currently I have infinity times 0, which is not a L'Hopital's rule case. L'Hopital's rule, I need it to be a fraction. So I need to move one of those two functions to the bottom. How could I move one of those two functions to the bottom so I could write it as a ratio? How could we move the x to the bottom? Yeah, just do a negative exponent. So I'm going to write this, so I'm going to think, okay, well, what if I had natural log of this on top divided by x? I want it to be a function divided by a function. If we plug in infinity now, does that work? No, wait, sorry. This has to be x to the negative 1, right? If I put it on the bottom, I need a negative exponent. If we plug in infinity, what is the top approach? 0, because it'd be ln of 1, which is 0. If we plug in infinity on the bottom, keep in mind x to the negative 1 is 1 over x, and 1 over infinity is 0. So it is a 0 over 0 case, which is good, because we can apply L'Hopital's rule. Okay, L'Hopital's rule says take the derivative. So we're going to take the derivative of the top and the derivative of the bottom. Don't bother simplifying the derivative. So on top, the derivative of ln is just 1 over all of the inside stuff. But then I have to multiply by the derivative of the inside. The derivative of 1 over x would be negative 1 x to the negative 2. Okay, so I've taken the derivative of the top. Then you divide by the derivative of the bottom. Look how great that is. The derivative of the bottom is negative 1 x to the negative 2. What can we do? Those are exactly the same. It was a product, so we can just cancel those out. If we plug in infinity now, you'd have 1 over infinity, but what's 1 over a giant number? 0. So this piece is approaching 0, so we get 1 over 1. So we get 1. Okay, 1 is not our answer, but we're really, really close. Remember this other side, we had ln of y. At the beginning of the question, we just decided to introduce natural log. We chose to do that because we wanted to bring the power down. So now we have to undo it. How do I undo the ln? E. So I'm going to take e to both sides. So it turns out that we have e to the first, or e. So this limit is equal to e. So when we thought 1 to infinity would always be 1, well, here's a case where 1 to infinity comes out to be e. Okay, so one more example that's kind of long like this, and then the last couple go really fast. Okay, if we plug in infinity, I guess always check to make sure it's one of these indeterminate forms, but if we plug in infinity, we have infinity to the 0 power, which is an indeterminate form. So we know we have to investigate further. So if you have to investigate further, you want to, and I recognize that I have a variable in the base and a variable in the exponent. I want to bring that down. So this is where I'm going to introduce natural log. So I start by just saying y equals. I do the y basically just so I remember to undo the natural log at the end. Okay, so I start with that y equals. I left myself a little space because I know I'm going to take natural log of each side. The reason why I want to take natural log is to bring that power down in front. So I have natural log of y equals, the limit always stays in front, like in the very front. So the power comes down, but it's really just being multiplied by the natural log function. That doesn't quite look like a ratio, but I could rewrite those two pieces as ln of x divided by x. Because I want to see if this is a L'Hopital's rule question. If we take the limit of ln of x as x goes to infinity, what is that approach? What is the top approach? To the top, what is the limit as x goes to infinity of natural log of x? Infinity. What about the bottom? What's the limit of the bottom as x goes to infinity? Infinity, which is great because now we can apply L'Hopital's rule. Okay. If we can apply L'Hopital's rule, we just take the derivative of each piece. What's the derivative of ln of x? 1 over x. What's the derivative of the bottom? 1. If we plug in infinity, we have 1 divided by a giant number. And what's 1 divided by a giant number? 0. 0 is not our answer yet, because remember at the very beginning of this question, we took natural log, and we have to undo that. How do we undo natural log? E. We have e to both sides. E to the 0 is 1. Okay. I don't want to say 100%, but I really, really don't think that I've ever seen one of these on the ACT test. So we're going to be prepared for them because they could come out that. I don't think they can. Okay. And then this page, let me just show you this. This will go really quick. Okay. One of the easiest things about limits, though, is often you can avoid L'Hopital's rule or other things if you're just looking at that relative growth rate. So relative growth rate, like you know it's an infinity over infinity case, but you know one of the infinities is like bigger or growing faster than the other, then you don't have to do L'Hopital's rule. So of all of these functions that are listed, which one grows the slowest? All of them, well, not all of them, but which one grows the slowest? 1. So 1 definitely is. It has the slowest growth rate. It has no growth rate. It's a horizontal line. Which one next would be the one that grows the next slowest? It does go to infinity, but it goes not very fast. ln of x. ln of x, and if you want, just think of the graphs, right? ln of x looks like this. It increases, but it increases really slowly. It does go to infinity. Which one it goes to infinity next? The next fastest. Y equals x, so a linear function. And then what? So we've done that one, and that one. We're down to x squared, x to the 10th, or e to the x. Which one grows the next? What do you guys think I heard? X squared or e to the x? So it turns out if I were to graph this, x squared does this. At first it grows faster. E to the x, though, eventually grows faster. Whoops, I don't want that. It eventually grows faster. So an exponential function eventually does grow faster than any polynomial function. So it would go x squared, then x to the 10th, then e to the x. So as you go to infinity, the exponential always grows the fastest. Even if it was like x to the 100th and e to the x. E to the x eventually will grow faster. You can kind of think about this with L'Hopital's rule. If you had x cubed over e to the x, that's infinity over infinity, right? If I was taking the limit of this as x goes to infinity. If I took the derivative, I'd get 3x squared over e to the x, which is still infinity over infinity. So I would take the derivative again, which would be 6x over e to the x, still infinity over infinity. If I took the derivative of that, though, the derivative of e to the x is always e to the x. A polynomial eventually will have a derivative that's just a constant. So then if you take the limit as x goes to infinity, it's bottom heavy, the denominator is still going to infinity faster, so it would be 0. So exponential always grows faster. So the shortcut is this. If you have two functions that are both going to infinity, you ask yourself which one goes to infinity faster. Well, the bottom goes to infinity faster. If it's bottom heavy, it's always 0. And then you don't have to do L'Hopital's rule. And that's like what this is showing. So on example 17, we have a log function, log function on top, which, yeah, it goes to infinity, but it grows pretty slowly. And we have an exponential on the bottom, which grows really fast. So like top heavy or bottom heavy, which one goes to infinity faster? Bottom. So I always kind of think of this to myself. This is still a bottom heavy question like we do with polynomials. The denominator is going to infinity faster. If the denominator goes to infinity faster, it's always 0. So you could have done L'Hopital's rule, but it would have been messy. So if it's an infinity over infinity case, we usually can get by with just relative growth rates. But make sure it's that case. So here, if we plug in 0, we get e to the 0. And then we have to think about what's happening on the graph of natural log of x as we approach 0 from the positive side. As we approach 0 from the positive side on e to the x, where does the graph go? Negative infinity. This is basically like 1 over negative infinity, but what's 1 divided by a giant number? I think I heard it. 1 over negative a million is approximately what? 0. So that one is 0. Okay. So most of the time with limits, these are often multiple choice questions where you can kind of reason through it. But if you're doing L'Hopital's rule, yeah, we'll show those steps. So I think that they're pretty straightforward, but again, don't assume that you can apply L'Hopital's rule. So can we do L'Hopital's rule on number 1? What was that?
You don't need to.
Would we be allowed to? If you wanted to, would it work? What has to happen in order for us to be able to do L'Hopital's rule? What was that? Only in 2 cases. It has to be what over what or what over.
0 is 0.
Good. The only time we can apply L'Hopital's rule is 0 over 0 or infinity over infinity. If it's not one of those 2 cases, L'Hopital's rule does not work. Here we plug in 2, we get a 4 in the bottom. 4 is not 0 or infinity, so it can't be L'Hopital's rule. If you did L'Hopital's rule, you'd get the wrong answer. Okay, and then you can plug in 2 on top and you get 0. 0 over 4 is totally fine. So that answer is 0. Okay, so just be careful not to apply L'Hopital's rule when it doesn't apply. So your assignment 6-6, you guys have questions 1 through 25 and 27 through 32. So at first it seems like it's a really long assignment, but we just did problem 1. You can see some of them go really fast. There's maybe a couple where you have to do L'Hopital's rule twice, but for the most part, they're not too bad. You can use relative growth rate. So some of them you can do without showing any work. You'll notice questions 5, 6, and 7. Those are just a review. It's like the exact same question, right? Exact same function. You're just either approaching 0 from the positive side, negative side, or 0. So it's also just a big review of limits that we've done before. This row here, 21 through 24, it's like our last couple examples where you're going to have to take natural log to bring the power down. Okay. And then 27 through 32 are just a couple review questions. All right. So that's it. I'll let you guys work. I know you don't have a lot of time. Tomorrow is going to be a review day. So tomorrow we'll just take questions on this and then you guys get to just work on your review. Thursday will be a in-class practice. So I've put together a few multiple choice and free response questions. Your test is on Friday.